Hello and welcome to In Simple Terms with Satish. Today, let's understand how 3D printers turn digital files into real objects. Take a small broken drawer knob. On a screen, it is only geometry, curves, holes, edges, and dimensions. A few hours later, you can hold it, screw it in, and use it. That feels like the file became matter. But the hidden hero is not the nozzle, it is the plan. A 3D printer does not understand a shape the way we do. It cannot look at a model and simply think, make this. It needs thousands of tiny instructions. Put material here. Do not put material there. Move this fast. Slow down on this corner. Heat the plastic this much. Leave empty space inside. Hold this overhang up until the part can stand on its own. This is why 3D printing is also called additive manufacturing. Traditional machining often begins with a block and cuts material away. Additive manufacturing begins with empty space and adds material only where the object needs it. The journey starts with a digital model. That model can come from design software, a 3D scan, or even medical imaging. But a perfect digital shape has no gravity, no cooling problem, no weak first layer, and no nozzle size. The real world does. So the model goes into slicing software. The slicer cuts the 3D object into many thin horizontal layers. If the layer height is 0.2 mm, a 40 mm tall object becomes about 200 layers. Then the slicer writes the machine recipe. It decides the outer walls, the inner fill pattern, the support structures, the travel moves, the temperatures, and the speed. That is the key. The model says what the object should be. The slicer decides how the object can survive being built. The printer follows that recipe. In a common desktop printer, plastic filament sips on a spool. A motor pushes it into a heated hot end. The plastic softens, exits through a tiny nozzle, and lands on the build plate as a thin bead. The nozzle moves across the layer. Then the machine shifts slightly and starts the next layer. Each new bead must bond to the one below it. That bonding is where the digital dream becomes a physical object. And it is also where prints fail. If the first layer does not stick, the whole job can become a mess. If the plastic cools unevenly, the part can curl or warp. If layers do not fuse well, the part can split. If a design has a steep overhang, the printer may need temporary supports because it cannot print into empty air. Infill is another clever trick. Many printed parts are not solid all the way through. The slicer can create a grid, triangle, or honeycomb-like pattern inside, saving material and time while keeping enough strength. Different printers use different physics. Some use liquid resin and light, curing one layer at a time. Some spread powder and use a laser, heat source, or binding liquid to fuse selected areas. Metal 3D printers can melt fine metal powder into strong parts with shapes that would be difficult to machine. The methods differ, but the pattern stays the same. Digital model, sliced layers, controlled energy or material, bonding, and finishing. A printed object is not automatically done when the machine stops. Supports may need removal. Resin may need more curing. Powder may need clearing. Metal parts may need heat treatment or machining. So 3D printing does not remove manufacturing discipline. It moves more of that discipline into software, material science, and process control. The useful mental model is this. A 3D printer is a robot that turns geometry into a sequence of physical commitments. The file is the dream. The slicer is the engineer. The printer is the patient machine that makes the dream survive gravity, heat, and time, one layer at a time. If this helped you understand the topic in simple terms, follow or subscribe to In Simple Terms with Satish and share this episode with one friend who likes technology. I will see you in the next episode.